Lerke, we cannot hear you. Well, no problem. In this case, let me introduce you the webinar, and we can then start. So this webinar is entitled Architectural Integration of 5G-enabled Industrial Networks with Edge Computing for Smart Manufacturing. We are going to have two speakers. On the one side, coming from Ericsson Research in Budapest, Dr. János Harmatos is going to talk the first part of the webinar. He is a senior researcher at Ericsson. He received his PhD in communication networks from the Budapest Technology and Economics University in 2005. And his research experience in the area of mobile backhauling, 5G network support, factory automation, service orchestration in a multi-domain, multi-provider ecosystem. In the last years, he has been contributed to several standardization forums, 3BP, ETSI, and 5G CAA. And currently, he's working on the system integration of 5G-enabled industrial networks on edge computing. Then the second part will be driven by Dr. Markosz Maliosz. He is associate professor at the Budapest University of Technology and Economics in the Department of Telecommunications. He is doctor from 2006 and in the field of communication systems. He is working as a guest researcher and consultant at telecommunication company in the areas of network performance, in different subsystem application, and his research interest includes network architecture and design, optimization, traffic engineering. He is currently focusing on network virtualization optimization, and he's author of more than 40 publications on the topic. So with this, I will give the floor to Dr. János to start. And before that, let me remind you that the meeting is recorded. We are going to have all the chat open during all the session. The chat, you can be asking questions during the presentation. In case the questions is easy, we could reply directly to the moderators through the chat. Otherwise, it will be handled in the research and questions part that will be at the end of the presentation. In case you want to raise your question in voice, you should ask for it and raise your hand, and then I will give you the floor to open your microphone and you will be able to talk. As I said before, all the recording will be available, including the slides, in our YouTube channel. Thank you for your attention, and now all the floor is yours, János, to start with the presentation.
Okay, thank you very much, Jose, for the introduction. And let's get started then. In the beginning, I would like to give a very brief overview of the 5G Smart project. So 5G Smart, 5G for Smart Manufacturing project is coordinated by Ericsson and ABB. And this project is started in June 2019. And now we are very close to the end. And the main goal of the project is to showcase how the 5G network could help to evolve the industry and manufacturing ecosystem. And we can say that the project has three main pillars or areas. In the first one, we have studied the different business models and impacts and manufacturing use cases and deployment options. In another very big activity, the goal was to demonstrate, evaluate, and validate the capabilities of 5G in different field trials, in different real manufacturing environments. So here we have demonstrated how 5G could be used for enhancing the industrial robotics applications. For example, here we have demonstrated a use case on cloud-based mobile robot control, but we have different trials in the areas of industrial manufacturing and semiconductor factory automation. And The third pillar area where we have studied the different enhancement or study how the 5G could enhance the smart manufacturing, and in this area we have studied the different networking integration options, TSN and industrial ones, and how 5G non-public network could be integrated into a factory ecosystem. And in this track, we have studied the different integration options between the network and the cloud domain. So the content of this presentation is fitting to this area, the third one, enhanced 5G for smart manufacturing. And the outline of the presentation, we will start with a very brief intro to edge computing, and I will give a very short background to 5G non-public network options. And then in the first bigger block, I will talk about the characteristics of different deployment options for 5G MPN and edge computing interworking and integration. In the second part, we will go deeply in the area of reliability. We will have a case study on how the TSN and cloud reliability features could be used in an integrated way. And in the third block, my colleague Markosz from the university will talk about the cloud management capabilities to support the industrial grade edge computing. So let's start with a short intro to edge computing. Edge computing provides an ecosystem where the execution environment, compute storage, memory resources, is closer to the location where the data is generated or consumed, in contrast with the remote or central cloud deployment. And this proximity of edge premise results in reduced latency between the client and the server application. So the edge computing can support use cases where low or bounded latency and optionally high reliability characteristics are required and crucial. And concentrating on the manufacturing area, one typical usage of edge computing in smart manufacturing could be to perform the compute-intensive tasks on the edge. So, for example, those application which requires AI ML mechanism could be deployed at the edge premise. But furthermore, edge computing enables the offloading of some latency-aware device control functions from the device to the edge. And for this offloading, here is an illustrative example from the 5G Smart project from a real trial where we have a cloud-based collaborative mobile robotics use case. So in this case, there were multiple mobile robots which were coordinated from the cloud in a collaborative way. And here we can say different scenarios for the offloading. So in the first case, only the high-level control functions were offloaded from the device to the edge, the trajectory control and the localization. But in the second case, we can say that the low-level time-critical servo control functions could also be offloaded to the edge. So this offloading enables a collaborative device control, but also enables to decouple the control system and the physical platform of the device. And these could evolve separately. And I mentioned that compute-intensive tasks can be performed on the edge, which can result a longer battery life in, for example, in this mobile robotic case. But this feature could be leveraged, for example, in an AR use case. And regarding the integration, so integration happens in the networking segment. So we can talk about the 3GPP activity, about the integration or the support of TSN by 5G networks. So there's a 5G TSN integration track in 3GPP, but in the 5G ACIA, there is a 5G integration with the different non-public deployment options. So some kind of integration is ongoing in the networking segments. But if we consider end-to-end point of view, that it's important to emphasize that the edge computing, the integration between the network and the edge computing domains are important. So that's why we have done this activity in 5G Smart. And because I will talk about edge integration with different non-public network options, here is a short intro to different 3GPP MPN types. So according to 3GPP definition, non-public networks are intended for the sole use of private entities such as enterprise and may be deployed in a variety of configuration utilizing both virtual and physical elements. And 3GPP defines two main types of MPNs. The first one is the standalone MPN. In this case, all 5G network functions are located in a certain enterprise premises, for example, in a factory, and the complete 5G network infrastructure is separated from the public network. And in this case, the industrial party or a third-party integrator is responsible for operating and maintaining the SMPN as an SMPN operator. And this kind of deployment would be the most favorable, I mean, for the factory deployments, because everything is local, and this kind of deployment could be integrated with the wired industrial network segments, for example, the TSN network. The other option where there are sub scenarios is the public network integrated non-public network. In this case, there are two options which can be seen on this figure. In the first case, only the RAN is shared between the public mobile network operator and the PNI MPN. But there is another case when the control plane is also shared, or we can say that the control plane is provided by the public MNO. So in this case, some functions are provided by the public network, but it's important to mention that the user plane still remains at the factory premise, so low latency can be guaranteed even in this case. And there are another option of the PNI MPN. This is the MNOHosted PNI MPN. In this case, all user plane and network plane functions are deployed in the public network. And in this case, all traffic is routed via the public infrastructure, so it should be considered. And the separation of the public and the MPN segments can be ensured. For example, the usage of network slicing. And now let's start with the first bigger part, characteristics of different deployment options for 5G MPN and edge computing integration. And as I mentioned, SMPN will be most favorable. So we have concentrated on the SMPN. And the first in the first scenario, there is an SMPN network and an edge computing domain for the industrial, for the virtualized industrial applications in the factory premise. And what I would like to say at the beginning is that in this scenario, the infrastructure for the network and the edge is totally separated. So this provides the most isolated deployment for the edge infrastructure and provide the most or the highest level of isolation for the latency critical industry control applications. And this, from the edge deployment perspective, this scenario enables the most flexibility because the different deployment options are possible. For example, single or multiple data centers could be deployed in the factory. Next slides will show example for this one. And I mean, the most important characteristic of this solution is that the edge owner has a full control on the full deployment. So in this case, customized solutions can be applied very well, which means, for example, if the infrastructure hardware needs to be accessed in order to deploy special industrial application, then it can be done without any problem in this scenario. However, in this case, there is not only flexibility but responsibility. So the edge owner should handling the full edge cloud stack, including the proper handling and in some cases design of the infrastructure layer in order to provide low latency and high availability, reliability capabilities. And it's also the task of the edge owner to maintain the virtualization platform, for example, the container runtime environment, and maintaining the cloud orchestration system. So this slide shows an example for a single standalone data center in the factory premise. So this option, I mean, this is the simplest one, and this suitable for support different collaborative industrial control scenarios. So mobile robot fleet control or collaborative fixed and mobile device control. In this case, each component of an application runs here locally at the edge. And what I would like to emphasize here that even if we have a single edge infrastructure and a single edge location, but even in this case, a multiple execution environment could be deployed at the edge if this kind of deployment is needed to support various application requirements. So we could have virtual machines if some application requires virtual machines, but we could have a container execution environment if we have also containerized applications. The other option for this on-premise edge deployment with SMPN is when we have several many data centers in a factory premise. So in this scenario, the granularity of deployment could be different. So there could have data centers deployed in different buildings or even different production domains, depending on the requirements of the application and the ecosystem. And this kind of deployment enables to use a different data center infrastructure, platforms in the different edge locations. And one way is to handle the data centers, the different data centers as separate clusters from cloud management perspective. But another option is to handle them in a federated ways as a common but distributed edge cloud ecosystem. And this federated handling results a higher level of reliability because the different application instances could be deployed on different data centers. So even in this case, even a hardware failure tolerant system could be deployed. And the cloud management systems, for example, the Kubernetes, supports this kind of federation of different data centers. So far, I've talked about cases when there was a separated infrastructure for the network domain and the compute domain. But with SMPN, we could have another deployment when there is a shared infrastructure which can host both the virtualized non-public network components, including the RAN, the core network, the UPF, and even the control plane. But the edge application cluster for the industrial application can also be hosted by this infrastructure. So this option ensures a more integrated operation or more integrated scenario by providing, or not providing, but we can use a single orchestration system for managing the non-public network and the compute resources in an integrated way. And we could have a common exposure API when which can be used for expose the capabilities of the networking domain and the compute domain in an integrated way. And we can use different cloud service models. In this case, for example, infrastructure as a service, where the customer or user of the edge ecosystem can create VMs, install the OS, and so on. But we can use platform as a service when a platform is provided, and the customer can deploy and manage its application. And this solution fits not only for the SMPN, but here PNI MPN option, which shared and control plane scenario could also be applied. And this is shown on this figure. And what I would like to emphasize here that this kind of PNI MPN deployment enables the mobile network operator to step into this kind of ecosystem, because not only the control plane can be provided by the mobile network operator, but the mobile network operator can host and provide this integrated exposure API, and the orchestration platform is also can be offered by the mobile network to the enterprise customer. And here I would like to show a scenario when we have an MNOHosted Edge and an MNOHosted PNI MPN network. So in this case, the large footprint of the mobile network operator can be leveraged, because the geographical density of point of presence of the mobile network operator, typically it means the radio access sites, the base stations. So this geographical density enables the deployment of edge premises, even in a, let's say, 10-kilometer range from the end devices, and considering the URLLC and other features provided by the 3GPP, and combining with the edge computing services which can be offered by the MNO, this use case could also support some industrial scenarios which needs not ultra low but low latency requirements. And in this scenario, different edge computing service options are possible. For example, the MNO itself may act as an edge service provider, and it deploy its own edge platform by using its own infrastructure, connectivity, and compute storage. And the MNO offer this managed service as a platform as a service directly to the customer. But alternatively, the MNO can offer its infrastructure to third-party edge service provider as an infrastructure as a service, and then this third-party edge service provider can offer a platform as a service for the customers. And what I would like to mention here as some difficulty for the customers, that if customized solution are needed in this case, that could be problematic, because probably the MNO will not give direct access to, for example, to its hardware infrastructure. So those kind of application which requires a specialized hardware access or hardware support cannot be deployed really in this case. Okay, so this was the first part about the integration of NPN scenarios and edge computing, and then I would like to say some words about a framework for the integration of TSN and cloud reliability. So first about TSN reliability. The IEEE TSN 802.1 CB specifies the frame replication and elimination for reliability feature, and this provides a mechanism where the frames are duplicated and transmitted over multiple communication paths between the TSN talker and the listener by using independent network resources. And the mechanism provides the elimination of the duplicates when necessary. And the essence of the operation that at the source node a certain TSN frame is duplicated and the sequence number is assigned to the duplicated frames. And then at the destination nodes, based on these sequence numbers, the replicas can be identified and discarded. So that's what is working on the network side. And in the cloud segment, we have studied the available mechanism because there are built-in mechanisms for failure handling in the cloud domain. And there are options where the active or hot standby application instances could be used to handle a failure case. But we have found that the time scale of these mechanisms does not meet with the requirements of industry use cases. Therefore, we have concluded that to provide the seamless end-to-end communication from a cloud-based application, multiple active application instances should be deployed in the cloud segments. And the active in this context means that each application instance will receive the incoming data. Each application instance will generate the required data for the industry device. And if we have multiple application instances running in the cloud, then from the device perspective, we can distinguish two main cases. In the first one, the industrial device is capable to handle multiple application instances. And in this case, a paired domain reliability can be set up. So we can have a pair application instance TSN FRARE function or component in the cloud domain, and we could establish different TSN streams for handling the duplicated packets by using independent resources in the TSN domain. And this kind of configuration can be done by the central network configuration elements of the TSN domain. And in the cloud side, this is rather an orchestration problem, because what we should ensure in this case is that the application instances should be deployed in a way that they use independent resources in the cloud. But defining the affinity, anti-affinity rules in the application deployment, this is possible. And what is also required is that the connection of the application of a certain application instance and the related TSN FAIR components should use independent resources within the cloud domain. And what I would like to mention here, that this kind of deployment, when the device is capable to handle multiple application instances, can be realized without the TSN FRARE mechanism, because in this case, a single connection per application instance should be established between the cloud domain and the device. What is needed is to ensure that these TSN frames use different resources in the TSN and in the cloud domain. And in this case have a device impact because the uplink frame should be replicated towards the multiple application instances. The other case, when the industrial device is capable to handle a single application instance, this could be a typical brownfield deployment when the device control software is just moved to the cloud and run in a virtual machine, but the software is not a cloud native, so it's not written, so the original software is used. And these cases, so in these cases, typically a device is accept control frames only from a single application instance. So to realize this case, it is required to hide the multiple application instances which are deployed in the cloud domain from the device by emulating a single application instance and the related Ferrer function. So this is deployment view of a certain application deployment with the multiple application instances and the multiple TSN functions. That here is the emulation view when the device at a given time see only a single emulated application instance and the related TSN functions. And in order to fulfill this kind of emulation requirement, the TSN Ferrer functionality is required to be virtualized and move to the cloud domain. Here we have proposed the TSN interworking function, which contains this virtualized Ferrer functionality and contains other functions which are used to support the emulation of the single application instance. So this is the detailed architecture view of this deployment and the details of this TSN interworking functions. So in the cloud, we have separated TSN and application cluster deployment. And in this case, the virtualized TSN functions are managed by the TSN controllers, while the application instances are managed by the cloud orchestrator. And this kind of deployment enables to minimize the interference of these two clusters if there is any change in one. And the TSN interworking functions is used to ensure that only one frame is sent towards the end device. The other frames from their application instances will be blocked, and these emulation support functions enables to assist the coordination of which application instance will serve the client device. And this helps that the application doesn't really need to care about the selection of which of them will be the serving instance, but this kind of selection is provided by this subfunction of the TSN interworking function. And if some kind of address translation, MAC address or IP address translation would be needed, that also could be performed by this interworking function. But the essence of this option is that if the device can handle only a single application instance at a given time, that this kind of virtualization of the TSN FRARE function is required in order to provide the proper emulation of the single instance which talks about the device. And now I will give the word to Markosz, who will continue the presentation with the cloud management capabilities to support industrial grade edge computing.
Okay, thank you, János. Hello, everyone. Now we jump into some Kubernetes-related technological details. So we think that container-based technologies for software applications provide a very good way to install, package, and build and run applications. And these advantages could be incorporated into the industrial area as well. And as containers, considered as a very lightweight application shells, so to say, and also portable. This brings that kind of advantage that if there is an edge computing domain installed at the factory, then, and if the applications are packaged with containers, then this gives an independency from the underlying hardware resources. Therefore, containers bring or reduce the integration burden of the software applications from the hardware environment. Supported by the Cloud Native Computing Foundation, Kubernetes is an emerging orchestration platform and considered in many cases a primary choice for container orchestration for general cloud-based deployments. For industrial usage, there are even lightweight and small footprint versions of them that could be ideally applicable into the edge domains. They have, of course, very common and important features that could be leveraged from the industrial applications as well. Among others, this scaling and failover to some level, and big advantages that different deployment patterns can be defined in Kubernetes. And basically, these are defined by some descriptor files, and they are interpreted by the system, and they are predefined patterns that could be mapped to the requirements of the applications. For the terminology later used, so more already presented by János as well, that in the Kubernetes terminology, a node is a server that is running containers, and actually containers are within so-called pods, where these pods are providing a so to say virtual host for those containers, or even it can contain a single container as well. So in the following, I'm going to get into the details that what are those points in a Kubernetes system that could help to be deployed and used them in industrial environments. Some of the questions was already mentioned by János, but let's see some more details now. Okay, thanks for the paging. So let's start with so-called infrastructure accelerators. Infrastructure accelerators are basically hardware devices that provide some kind of specialized functions. These specialized functions relate to either they provide some quality of service guarantees, or they have some special functionality. The problem with them is that if we run some software within a virtualized environment on an edge cloud, then these hardware devices are restricted from the virtualization environment. So this solution that Kubernetes has is a so-called device plugin framework. Actually, it is in a beta stage, so still under development. The goal is that, as I mentioned, that if you describe a deployment with Kubernetes objects and descriptor files, then you don't need to modify anything within that, but you already can use those devices. The most common solution to use these devices is to bypass the nodes system software and the virtualization layer, and that is what is guaranteed by the device plugin framework. One drawback is that for that specific devices, it has to be implemented by the device vendor. In our case, so in general case, they either offload some computation from the central processing unit. For example, this is true for the graphical processing units, GPUs, or they have some special functionality like the network interface cards that, for example, have some TSN capabilities that are supported by hardware. For example, you can specify the transmit time of the frames, which are adjusted to the hardware clock of that network interface card. So basically, the operation is the following: that if such a node has some specific devices like this TSN-capable network interface card, then it will advertise these resources towards the pods that run the application components. And the device plugin will be able to announce these capabilities, and the system component that runs on the Kubernetes nodes, which is called the kubelet, interacts with this device plugin, and the device manager can interpret the workload description if that kind of workload, the pod container, would like to use a specific device. Of course, as you can see here, the usage of these specific devices are a scarce resource, so it also has to manage that if there are such devices, the access arbitration need to be handled by the device manager as well. Basically, we can use such specific network interface cards as the TSN talker or listener component that was depicted in the figures of János as well. So that is a feature that supported by the Kubernetes, and actually those nodes that contain these specific devices can be labeled by the system, and that leads to the next feature of Kubernetes. Could you please page it? Thank you. So this is the placement of application components that is managed by the Kubernetes. These rules are managed by or described by affinity and anti-affinity rules that can relate to either nodes or pods. This is a major feature of Kubernetes, so it could be used. It is not a beta compared to the device framework. And when we specify a deployment, then among others, this description can specify how many instances do we need to run from that application instance, what are the rules for scaling, for example, and so on. And among others, we can also specify these affinity and anti-affinity rules. Let me show you an example that if we have some nodes that have those specific network interface cards that are managed from the device plugin framework presented in the previous slide, then we can assign node labels to those nodes. And from now on, the system will keep track about these labels. And the affinity and anti-affinity rules can be divided in two parts. So if we need a application that has to be accessed that specific device and specific node, then we specify the node affinity rule, and the node affinity rule will relate to this node label. And if we want to distribute them, provide the independent disjoint placement of those TSN functionalities, then we have the pod level anti-affinity rules, because we can specify that if we have placed a TSN capable pod on a node that has the appropriate label, there cannot be placed another pod on the same node. So only one can be placed, which also incurs that another node should be taken or selected, which has also this label with this TSN NIC capability. So these rules define not only, or can define not only this specific situation, but basically they could be formulated for all the different cases presented in the previous slides. So basically, this capability can be used as a major feature, and even today these are used widely for another specifications as well. Of course, if there are not available nodes for these labels, then of course the deployment will not run to success. This means that the dependency of the available hardware devices need to be taken care by the system operator. Okay, we can jump to the next slide, please. So this slide is about the built-in Kubernetes resiliency and self-healing methods. It can be divided into two parts, because we see that the external world and the internal world of the cloud platform is handled differently, is divided. So if the request handling that comes from the external networks towards the applications running within the Kubernetes, then the typical solution is that we have a hardware load balancer that distributes the traffic between the nodes that are running the application instances. However, after that, we have an abstract object, which is called the Kubernetes service, which again redistributes the requests that arrived from the external world. So it can also, or it does also, a load balancing among the pods. So that's the difference, that the service does the distribution among the pods. while the external load balancer does this among the nodes. This is the basic operation of the service, which means that an application instance is selected arbitrarily that could handle a request. The resiliency methods that are built in, self-healing, is managed by the Kubernetes system because it monitors the status of the pods. And in addition, in the deployment descriptors, we can also specify different probes that also can test the liveness of the applications. However, the problem with this is that the minimum interval that can be set up for these probes is 1 second, which is quite good for an IT operation which can tolerate longer disruption times, but not for a industrial application. And that's why we think that this is a missing feature where we can do a similar operation which is done with the TSN frame replication, that multiple active application instances could be handled by a specific Kubernetes service object, which is not yet defined and implemented in those systems. So that we see as a capability gap. Okay, we can jump to the next slide, please. For the networking aspects, there are also some interesting points. Because again, this Kubernetes service, as I mentioned, that does the load balancing in between the pods, actually does everything at the IP level, layer 3, doing IP routing and IP tables, rules, network address translation, which is good for a general application that runs at the IP level. However, if we want to get a direct layer 2 traffic, TSN traffic, into the cloud domain, then the typical option is that we need to have to manage another secondary network, because by default all the pods have one network interfaces. Fortunately, Kubernetes has a way to handle this. There is a so-called meta plugin. The name is Multus, which provides this capability that we can define multiple virtual Ethernet ports to the same pod. And the way that we can just lead in this network and just omit the Kubernetes service and the layer 3 IP traffic handling is to define our secondary network and map them to our applications. And the most promising solution is if for this secondary network interface, we use the so-called Mac VLAN plugin, which is basically will use the node's node network interface card and map it to the application instance. Basically all the application instances can have, even if they within the same node, have different MAC addresses and also IP addresses, but as they have different MAC addresses, they can be addressed directly at layer 2 level. One more aspect which is often arising in industrial environments, that different network segments has to be defined, that they are separated from each other. Kubernetes fortunately has also a solution for this, because these so-called container network plugins support the separation by a so-called namespaces. These are the namespaces defined within Kubernetes, not the Linux namespaces. And a one-to-one mapping can be done in between the two. Next slide, please. And about resource management, because we suppose that the TSN network can handle the strict timing of the frame delivery. However, when we enter into the edge computing domain, we are basically switched to software switches, virtual Ethernet interfaces, and so on. So the question is, what can we do at the software resource management level? And Kubernetes also has a beta feature, which is called the CPU manager. Basically, we want to protect our application from noisy neighbors. And this CPU manager provides that capability that some of the CPUs can be used only for specified applications, in our case, industrial applications, and they are running in the exclusive pool. And in addition, these applications will be in a so-called guaranteed quality of service, and they will get a whole CPU unit that guarantees that there will be no interference. Of course, another set of the CPUs could be used in a shared pool, in a shared way, where they compete with each other for these CPU resources, and also some of the CPUs could be reserved from the Kubernetes system. Kubernetes, which manages the CPU and memory resources for the pods, uses or are in interaction with the completely fair scheduler, which is one kind of task scheduler on the Linux, and this is the default one. These settings can be managed from the Kubernetes deployment descriptions. Unfortunately, so this scheduler is for high throughput and fair scheduling, and it cannot really prioritize industrial applications with strict timing requirements. Therefore, the recommended way to do that on the node level has to be made some changes, because all the processes, even if they are running within the containers, they are the processes of the nodes, the host operating system, and there are some settings that the response time and the real-time operation or near real-time operation of such systems could be improved. Of course, this is not strictly Kubernetes related. It can work on any system. What is recommended in most of the cases to disable the power management in the basic input-output system at the nodes, because the different sleep states that are enabled by this power management can just ruin the response times and make them prolonged. And the other option, which is often recommended, is to update the normal Linux kernel to the real-time extension Linux kernel, because that guarantees better and manageable response times and goes for prioritizing the critical tasks. So basically, these are the options that could be used, integrated in a Kubernetes system that would be or should be applied in an industrial environment. And now I give back the word to János for the summary.
Okay, so some brief takeaways. We have shown that there are numerous integration or combination options of different 5G net, MPN and edge deployment alternatives. So we have only showed some illustrative examples, but what we have found is that in most of the cases, we need a decision between the flexibility and customizability and the simplicity, because if we need a customized or customizable solution, then it means that the owner of the deployment should have deep knowledge in the networking and in the cloud part. On the other hand, if we have a third-party offer, the managed solution, then in this case it is not easy to deploy such an industrial application which requires special, for example, hardware support or so on, because these kind of features can be used in a limited way in a third-party managed solution. And on the other hand, Markosz mentioned that Kubernetes platform has some built-in and available capabilities to support the different industry application deployment cases. However, we should mention that originally Kubernetes was designed for handling the web service type application. So we can say that some special extensions and add-ons are required to provide a platform level solutions and support for industrial use cases. And now we are at the end. And I mean, so at first, thanks for listening. And then we have now time for questions.
I can inform you, János, thank you, that there are no questions in the chat. So if anybody wants to make a question in the audience, just please raise your hand and I will give you the floor to talk. No questions. 30 more seconds just to see if someone wants to ask something. Okay, this means, János and Marios, that you explained so well. That is crystal clear for everybody. More than 40 people connected and was attending the presentation. Thank you so much to the two presenters. And as I said before, this presentation will be available in YouTube for your scrutiny in the future. So that's all from today, and thank you so much.
Okay, thank you very much.
Bye-bye.
Thank you for the attention.
Thank you.